Alright, welcome back to the Cymax channel. Last time we talked about this Tennessee Eastman process simulator. This runs in Hugging Face and is a good tool for visualizing what happens in the feed flows, the reactor, the separator. You can introduce faults over here, and I showed you can download a CSV file of the data. But you might want a different way to interact with this, and I'm going to show you the next step today. So if you click on the GitHub repo that has all of this code in it, there is a Colab that you can click on here, and this will open a Google Colab that connects to, or where we will install the Tennessee Eastman process simulator. And so I'm going to show you a couple of things here that are the beginning of a Python interface to the simulator. So the first thing we have to do in Colab, and probably where you're working if you try to do this locally, is we have to install it. So I'm going to go ahead and start this. These are the directions. This is not on PyPy. I don't know if we can put Python and Fortran with compiler stuff there, but you can install it directly from GitHub and get the latest version. And you have to specify this Fortran enabled and make sure you have a Fortran compiler. Otherwise, you'll get the pure Python version, which should also work, but it's about 10 times slower. So this will go through, it clones the repo, it's going to run the build commands, and if it all goes well, when you're done, you'll have TEP installed, and we can check that we have what backends are available. So we have Fortran and Python. The default will be Fortran. It is, as I said, 5 or 10 times faster than using Python. So then there are a couple of examples here. We'll start with just a simple simulation. This one sets up a TEP simulator. You can specify a random seed that should give you reproducibility. We initialize and then make a measurement. And this one's super simple. It just gives us a few of the measurements. This variable actually has many things that are in it. If we look at XMES, there are a lot of numbers that correspond to all of the things that are measured, and there's some documentation in the package for that. We can also run a 2-hour simulation, say with no faults. So here we specify a duration and when to record information. And then we'll make a plot down here that shows some of those variables. So here we get the measurements, they're on the result object, the time, we plot them. We have to know a few things about which measurements correspond to pressure and reactor level. Again, that's all in the documentation. And then you can see here we have graphs that you can use. If you want to put a fault in, we can simulate this as well. We can import disturbance names, and it's probably worth mentioning here from TEP import measurement names. These are all of the measurements that are recorded, so you can see what those numbers correspond to in this list. Similar for the faults. These are the fault names. We'll look at the step change in reactor cooling temperature. Next, we can create our simulator. We introduce disturbances like this. This says introduce disturbance 4 at t equals 1 hour. So we can go ahead and run that, and we can see that it does onset at 1 hour, doesn't cause a reactor shutdown, and here we can plot this as well. And here you see where the fault was onset. The reactor pressure starts going up. There is the step change in the reactor valve, and so we can see other things there. There is 2 versions of control, closed loop and open loop. And so here we've been specifying closed loop. That means the controllers are all working. We have a disturbance in here, and if we do no control, then what we find out is that this process isn't actually stable without control. So With the closed loop, we don't get a shutdown. With open loop, we do. And you can see why when we look here, as it starts out kind of similar, but as soon as we introduce a fault, then the pressure goes up, and as soon as the pressure hits 3000, that's a safety criteria that makes the reactor shut down. All right, the last thing I want to show you is using a fault detection plugin system. I'll give you a very basic example, but you could try others. So we have a series of kind of standard fault detectors. I have not tested all of these. We're going to look at one of them and see how it works. So first we're going to run a baseline so that we can get some basic statistics, mostly the mean and the standard deviation. And then we're going to create a threshold that will tell us whenever samples get more than 3 standard deviations away from the mean that we have detected a fault. I'm only going to monitor one index here just to keep it simple and not have too big of a graph. So we run this, that gives us the standard, mean, and standard deviation. Now we can run a simulation. We'll do 30 minutes of normal time and then introduce fault 6 here. Let's see, how does that look? We create this, initialize, we store some variables, we go through the step, and we run this one step at a time, and then at each step we can run our detector up here, and we'll let that go. And then we can analyze the results. So we extract out our times and our measurements, whether we have a fault, and we can see that we do detect one. And then let's plot this so we can see what happens eventually. Down here is everything between these dashed lines is the plus or minus 3 sigma. Those are all going to be fault free. And then everything outside is considered faulty. So we have some fault range that's detected here and here. And then we don't have faults here and here because they fall between the lines, even though this is where the fault has occurred. That's just a limitation of this particularly simple threshold detector approach. If you were using other methods, they might, well, they should behave differently. And so here we can calculate, some true positives, false negatives, and get some information. Our accuracy is not that great, 82%, and we have a fault detection rate that is also like a little less good, and that's mostly because we have many false negatives. All right, that's basically it. Colab offers a different way for you to interact with the Tennessee Eastman process simulator, and you can try it out without installing any software on your own machine, but that's because you install it on Colab. If you did install it on your own machine, then you could do all of these things as well, and there's quite a bit in the examples to look at and try to figure out, what can you do in writing code. And next time I'll talk maybe a little more about the command line interface, which is something that works well locally. All right, that's it.